discuss the many ways that have been proposed to detect axions, in particular to detect axion dark matter, but also solar axions and axions in the laboratory. Then I want to actually talk about particular properties of axion dark matter, that they form a Bose-Einstein condensate. And actually I want to argue that axions are not just a candidate, but that they are at least part of the dark matter. So I guess this is a very ambitious claim, and I hope you'll give me the appropriate challenges for such a big claim. So axions are motivated, before we get lost in the details, I want to say axions are motivated by particle physics because they solve a problem in the standard model called the strong CP problem. They are present, as actually pointed out, they're present in many models of beyond the standard model physics, including supersymmetry and string theory. They're a form of cold dark matter. And then also, close to my heart, axion Bose-Einstein condensation explains some observed properties of galactic halos. So let's start with the strong CP problem. The standard model, as you know, is a tremendously successful theory, yet it has a puzzle that is often swept under the rug. If you take the model as it stands, it doesn't give an explanation why the strong interactions conserve P and CP. In fact, let's see. Oops, sorry. What happened? Okay, back. So how do I point to the laser?
It's this one.
Okay, all right, okay. Thank you.
And the slides also move.
Right, thank you. So in general, to the Lagrangian of the standard model and of strong interactions, you can add this term, which is P and CP odd. It's like E dot B in electromagnetism, but it's in terms of the common magnetic fields. This term is generally present because in the standard model, P and CP are introduced by giving complex phases to the Yukawa couplings. And this explains CP violation in the weak interactions. But then you would then expect that this angle theta bar would be of order 1. And as it happens, it must be less than 1 part in 10 billion because the strong interactions actually conserve P and CP, and this limit comes from the upper limit on the neutron electric dipole moment. So to dramatize this statement, I like to introduce this pool table analogy, where the pool table is like the physics of QCD, which has higher symmetry than the standard model in which it is embedded. So this room violates left-right symmetry, but the table in it on which you play pool is left-right symmetric. And as a physicist, this is a shock because you would not expect that in a room that is askew, that the pool table would be horizontal. And you would be particularly surprised if the room were askew and the pool table is horizontal at the level of 1 part in 10 billion. So it really is a puzzle. So the standard model does not explain why this angle is so small while the pool table is so horizontal, but Péchet and Quinn invented a simple addition to the standard model called U1 Péchet-Quinn symmetry, which solves the problem if this U1 has the following 3 properties. It must be a symmetry of the classical action. It must be spontaneously broken, and it must have a color anomaly. What happens then is that what was a parameter in the standard model, theta bar, becomes a dynamical variable. The Nambu-Goldstone boson associated with the spontaneous breaking of the U1 symmetry of Pichet-Quinn becomes this dynamical variable. It's this A field, actually the Axion field. The Axion field divided by some scale with dimension of energy is the parameter theta bar in the low energy effective theory when there is a U1 symmetry. So that now theta bar becomes a dynamical quantity, and it can be shown that it will relax to zero, because actually Waffa and Witten showed that the effective potential for theta bar has its minimum at theta bar equals to zero. So if theta bar becomes a dynamical degree of freedom, it will just relax to zero. As Weinberg and Wilczek pointed out, this mechanism solves the strong CP problem, but it modifies the low energy theory by the introduction of a new particle called the Axion. It's a pseudoscalar particle, and it is very light. So if you had to solve the problem of why this pool table is so horizontal in a room that is skew, what would you have done? I only give you 3 seconds. But you could have come up with that if given enough amount of time. So instead of designing the pool table with legs that are adjusted to compensate exactly for the fact that the room is askew, you could instead build this contraption, which is such that the pool table will become horizontal no matter what is the skewness of the room. And this is in fact really analogous to the Pichet-Quinn symmetry. It is a way by which the angle, the misalignment angle, can relax to zero naturally, because there is a force, actually in this case it is gravity, in the case of QCD is a strong interactions, but here gravity tells you what is Q and what is not. And so you can use gravity to straighten out the pool table. Now, if you do this, and you are aficionado of pool table, you'll realize that this pool table is not an ordinary pool table, because the pool table can oscillate. And so also this pool table has an axion. The axion is the quantum of the pool table oscillation. Okay, now, if I may go back, the frequency of oscillation, h nu, times Planck's constant, is actually the quantum of energy in this oscillation. That's analogous to the axion mass. And this frequency becomes very low if the lever arm of the pool table is very large. And also in that limit, the pool table becomes very much decoupled from whatever happens on the pool table, because it's very difficult to excite the oscillation of the pool table if the lever arm is very, very long. Actually, all this has analogous things in Axion physics, because the analog thing to the length of the arm and the pool table mechanism is the Axion decay constant. If the Axion decay constant is very long, then the mass goes to zero. Actually, as befits any Nambu-Goldstone bosons, because the scale of Fa is the scale of symmetry breaking of the U1 symmetry of Péchet-Quinn. So when you take that scale to infinity, the mass goes to 0. And also all the couplings of the particle, the axion, go to 0 in the limit where the axion decay constant becomes very large. In fact, for a while in the early 80s, it was thought that you could solve the strong CP problem by a so-called invisible axion, because if you make the scale very long, very big, then the axion mass goes to 0. The strong CP problem is still solved as before, but the couplings of the particles are so weak that the particle is very difficult to detect. Now, let's suppose that you imagined you're playing pool on this. You're a pool player in this room, but you don't see the mechanism. The mechanism is hidden to you. But you notice that the pool table is horizontal. What experiment would you do to show that actually the pool table has been put straight by this mechanism? Well, you try to excite pool table oscillations. That would be the test. So you could, for example, hit this side with a ball, and then it would excite the pool table oscillation, and this ball would recoil, which should not happen in principle with a regular pool table. So this is like a beam dump experiment, because you produce an oscillation, and then the oscillation manifests itself. So in the beam dump experiment, you would dump a beam, produce axions, and then later the axions would manifest themselves. Many experiments were done to try to discover the axion particle. Beam dump experiments, as I just described, but there are many other attempts. In particular, rare particles decays, let me mention. So for example, the K plus kaon would decay to pi plus and an axion. This has never been seen. So there are constraints from that. The beam dump experiments never produced axions. There are radiative corrections due to axions, for example, to the anomalous magnetic moment of the muon. And then there's a very interesting set of constraints on the axion from the evolution of stars. So this conference is about dark matter, so I don't want to talk about the many other aspects of axion physics, but it has a very interesting effect upon stellar evolution. And this is because the evolution of stars is controlled by the opacity of the star. So there are nuclear reactors inside the star that produce energy, but the energy cannot escape because the photon that's produced in the hot core of a star has to rattle and will get scattered many times before it actually can escape. And so it's a nuclear reactor, but it is very well controlled by the size of the star. But if you have axions, they can be produced from the center of the star. They will escape immediately, and then the reactor will go quicker, actually. No, actually all these reactions will speed up, and the star will evolve more quickly, and it will have it will have a shorter lifetime. This is a very rich topic. I will say nothing more about it. I just referred to a slide from George Raffelt here, and here's constraints from the sun, from horizontal branch stars, from red giants, from the supernova, and so forth. So there are many limits actually from stellar evolution. The upshots of all the limits from stellar evolution and laboratory searches is that basically all axions are ruled out with mass heavier than something like 10 to the minus 3 eV or 10 to the minus 2 eV, corresponding to decay constants less than 10 to the 9 or 10 to the 10 GeV. So this is the scale at which Petri-Quinn symmetry gets broken. It should be at least as large as 10 to the 9 GeV. Now, you see it here that there is actually also a limit from cosmology. And this is very fortunate because otherwise there would truly be an invisible axion, because you could then, escaping these constraints, you could make the axion arbitrarily light and arbitrarily weakly coupled. But in fact, you cannot do this. And the basic reason for this is that the lifetime of the universe is finite. Because if you adjust a pool table by the pool table mechanism, it takes a certain amount of time for the pool table to relax. And if the lever arm is extremely long, then the oscillations are very slow. And relative to the age of the universe, the pool table will not be able to relax. And so that's the basic mechanism by which very light axions are ruled out, because the age of the universe is finite. So axions are different from other particles that were discussed, say, here this morning, like WIMPs. WIMPs are produced thermally in reactions in the very early universe. And actually, axions are also produced thermally. For example, yes, please, finally.
On the previous slide.
Yes, please.
The QCD axion, the FA has to be larger than 10 to the 9.
Yes.
That comes from...
Yes, so there's a lot of discussion. This is why I like to put this slide, because it's also difficult to read. Right, so actually the best limit comes from the supernova, 1987A. And what happens there is that people observe the neutrinos from the supernova, and the neutrino pulse gets quenched if there are axions, because the hot neutrino sphere inside the supernova would get cooled by axion emission, and you would not have seen the neutrinos in IMB and Kamiokande and so forth. But that's actually not the only limit, but it's actually a very nice limit because it involves the coupling of the axion to nucleons, because the axions are produced by interactions with nucleons, and there are very little model dependence there. There are also couplings there are limits from axions to electrons, but they are more model dependent. So the discussion is a little complicated if you look at all the details, okay? But roughly, it is something like 10 to the 9 GeV, the scale. But thank you for question. I want more questions, by the way. I feel kind of self-conscious just telling the story and no feedback. So on this slide, I was going to say that axions are also produced in the early universe by thermal processes. So at very high energies, if the axion decay constant is, say, 10 to the 12 GeV, at temperatures above 10 to the 11 GeV, gluon, quark collisions, and so forth, gluon-gluon collisions will radiate axions. And these axions will have the temperature of the bath at the time. And you can estimate actually what would be their temperature today, and it is roughly 1 degree Kelvin. There are, neutrinos are somewhat colder than photons, but axions are still a little bit colder, but the temperatures of order degree Kelvin. It depends upon how many numbers of thermal degree of freedom disappear after this decoupling and today. But axions are not only thermally produced, they are produced by other mechanisms related not to the temperature, but as I mentioned or suggested, related to the finite age of the universe. The axion mass turns on at a particular time, actually. The QCD effects that give the axion its mass are suppressed, it turns out, at high temperatures because QCD is asymptotically free. At QCD time, when the temperature is of order 1 GeV, the axion mass turns on. The size of the horizon then is 10 to the minus 7 seconds. That's the age of the universe then. This time is going to appear many times, T1. It corresponds to length. The horizon at QCD time is roughly 60 meters. There is a momentum associated with this horizon. So if this is 60 meters, the corresponding momentum by de Broglie's rule is 10 to the minus 9 eV. So if you look at the axion field at that time, you'll see it has very short wavelength oscillations associated with the temperature, and it has long wavelength oscillations associated with the horizon. And you see there are 18 orders of magnitude between these two scales. So these long wavelength oscillations are extremely cold, as we will see. So in this slide, I briefly go through the history of the universe. If Peche-Quinn are right, that the strong CP problem is solved by Peche-Quinn symmetry. Peche-Quinn symmetry is a U1 symmetry which is spontaneously broken. So it has an effective potential with the shape of a Mexican hat. But at very high temperatures, the symmetry would be restored. The critical temperature for the spontaneous symmetry breaking is the scale of symmetry breaking, actually, which is the decay constant. So at high temperatures above the decay constant, the symmetry is restored. Then at the Peche-Quinn scale, the temperature is sufficiently low that the symmetry gets spontaneously broken. But QCD, then the axion is still massless. Later at QCD time, the axion will acquire mass, and the bottom of this Mexican hat is called the Mexican hat potential. I don't know anyone wearing this kind of hat here, but sometimes on special days, perhaps. Okay, so this is flat above the QCD phase transition, because the corresponding to a massless axion. The axion is the degree of freedom at the bottom of the Mexican hat potential. Then at QCD time, this potential gets tilted, and the axion mass becomes finite, and the field begins to oscillate. And this is like pushing the pool table in the room that is now felt to be skew, and it begins to oscillate. And it wants to relax to zero, but it will take some time. I want to point out that there are actually topological defects associated with these transitions. There are strings associated with this transition because you have a topological defect, which is a string, which is such that when you walk around the string, you walk around this Mexican head potential at the bottom. And then you have walls, domain walls, which are when you walk through the wall, you go through this bottom once, but you come back. So you have on one side of the wall, you have vacuum. You walk through the wall, you go around, you come back to the vacuum. It's a stable object in 1 + 1 dimension. So it's a stable wall. Of course, the wall may be bent and it will oscillate in 3 dimensions. So some of us in 1983 estimated how much energy density would be today in the oscillations of the axion field started during the QCD phase transition. So above 1 GeV temperature, this Mexican head potential is flat. So this is now the bottom of the Mexican head potential represented as a line. It's flat at 1 GeV temperature, above 1 GeV temperature. Then below 1 GeV is curved, and the Axion field begins to oscillate. So it's a simple exercise to estimate how much energy density there is today. Sorry, today should be T naught. This is a typo, I'm sorry. So this is the number density at time T1 when the oscillation starts. And then you multiply this, the number after the oscillation has started, the number of axions is conserved. It's an adiabatic invariant. And you multiply by the axion mass, because they actually are non-relativistic, and you put in the appropriate scale factor, and you get the density today. And you find that the lighter the axion mass, the more energy density today. As you would maybe have expected with the pool table, the lower the frequency of oscillation of the pool table, the more there will be a relic oscillation in the pool table. After all, if the frequency were so low that the pool table only started to oscillate today, the full energy density would be in this pool table. It has no time to dilute. Anyway, if you look at this problem, you find that the energy density becomes larger when the axial mass becomes smaller, and the power is 7.6, apparently, of course. We don't know exactly. Now, this is so-called axion production by vacuum realignment. It turns out that you also have axion production by string decay. And I just show a simulation. The amount of axions produced by strings has been a controversial topic for many years, with people are giving estimates that differ by a factor of 30 even today. So I'm not going to go into this controversy. I just want you to be aware of it. I just like to show this picture of a simulation we did with Chris Hagman and Xionyun Chang of a string that is a loop, and it starts. So you actually it's an actually symmetric loop, and you just see here the cross section of the loop with the plane, and then we let go of it, and it begins to accelerate inwards because the loop wants to collapse. And what's nice about this is that you see the Lorentz contraction of the core of the string as it accelerates inwards. The scale changes. So now the loop has contracted to a point and now releases tremendous amounts of energy, and it just gets radiated away. So people have done simulations like this of different configurations to try and estimate how many axions are produced by strings, and they find answers that differ by a factor of 30. My own belief is that the string decay contribution is of the same order as that from vacuum realignment. Batti and Scheller gave it a factor 30 more, and Yamaguchi, Kawasaki, and Yokoyama are somewhere in between. Anyway. You also have domain walls, because if you have strings, when you go around the string, you go around the Mexican head potential at the bottom. But when the Mexican potential gets tilted, then actually you go through a domain wall, so that each string becomes the edge of a domain wall. And this would be a cross-section of the universe of strings bounded by domain walls. And we simulated this too with Chris Hagman. So here's one of these domain walls between two strings. We gave it angular momentum, and it turns and it collapses and produces a bunch of radiation. And this is also a contribution to the axion energy density.
So I have a question.
Sure.
We've got a visualization problem here.
Yes.
Trying to deal with the domain wall. Why do you have to go through domain wall when you tilt the
Thank you. Okay, I really appreciate. It takes a while to really visualize it correctly. Okay, first we break U1 symmetry. And what that means is that you can have strings. Can you see that? Here's a string. When you go around the string, you point in different directions of the Mexican head potential. That's a stable object for a straight string. Now you tilt the Mexican head potential, and now what happens is that you don't want to go around at the same rate of speed. You want to stay at the bottom all the time and then quickly go through. That is the lowest energy configuration. But you see that it is required that when you go around the string, you have to go around once, and that's the domain wall. Actually, so you're going to have, what's going to happen is that you're going to stay at the bottom, you're going to stay at the bottom all the time, and then you're going to quickly go around. There's going to be an optimal way to do that. That's going to be the domain wall, and then you're going to be at the bottom again. So I'm going to be a string at the boundary of a domain wall, and every string is going to be at the boundary of a domain wall. And then when you get to the QCD phase transition, so here are all these, I don't know whether this was clear. So here, this is a string going into the page. This is a string going out of the page. Okay, you see, so it goes around like that. And this is kind of simulation. You see, the significance of this is that all of these objects are finite size. And so they have a finite lifetime, and they all disappear. And you can estimate how much axions are produced. Okay, and so it's another wrinkle in this problem of axion production. So maybe I'm going a little slow. I thought I covered this. There's actually two possibilities. So when you go to Axion talks, they talk about post-inflation and pre-inflation Peche-Quinn symmetry. In this case, I assumed in making this description that inflation happens first and then the Peche-Quinn symmetry breaking, and then you have strings and domain walls. But you could imagine that you first break Peche-Quinn symmetry and then inflate. And the significance of this is while you inflate, you would homogenize the axion field over the whole visible universe. And so then there would be no strings and there would be no domain walls. And you have this uncertainty then because there is a single angle for the axion field that has been homogenized by inflation, and it's the same everywhere, so that it could be accidentally so that this axion field is aligned just at the CP conserving minimum. This is parametrized by this angle here, squared. So I didn't say it yet, perhaps I did, that the critical axion mass is of order 10 to the minus 5 eV. Typically, you'll get critical density in axions if the mass is of order 10 to the minus 5 eV, 10 to the minus 5 eV. But you could have this accidental suppression. If you have an accidental suppression, you could have smaller axion masses. So this is here then, I want to make the point, allude to the issue of isocurvature density perturbations. If there's inflation after Peche-Quinn phase transition, the axion field gets homogenized but you have quantum fluctuations in the axion field of order the Hubble constant during this inflationary scale. And these fluctuations turn into isocurvature fluctuations, and they are severely constrained by the CMBR. Okay, this is a somewhat busy slide. If the reheat temperature is less than the Péchyquin scale, you have constraints on the scale of inflation as a function of the axion decay constant. Basically, what is disallowed is to have both a large axion decay constant and a large scale of inflation. But for given axion decay constant, if the scale of inflation is sufficiently small, you're okay. Or else, you first had inflation and then Péchyquin phase transition. So it's a somewhat complicated set of constraints. If there's no inflation after Péchyquin phase transition, then you do have strings and domain wall decay. And this is my estimate for the relationship between axion mass and axion cosmological energy density. I should say that, of course, nowadays we think omega A is somewhat smaller because there's dark energy, not only dark matter. So that has tendency to push up the axion mass. Recently, there was a paper in Nature where they have modified this relationship by a factor of, I estimate, 2.4. But this paper only appeared 2 weeks ago, so I think this has not been fully digested yet. But there may be, if this paper is correct, it would tend to push the axion mass up for given omega A. And then I should mention axion mini clusters because if there's no inflation after the Péchyquin phase transition, then you have inhomogeneities on the scale of the QCD horizon that just expand with the expansion of the universe, and then they make mini clusters today. The typical mass is 10 to the minus 13 solar masses, which is like the mass of Mount Everest or something. And the size is 10 to the 13 centimeters, which is like one AU. So they are very diffuse objects in the axion fluid. Okay, so to summarize, axions are cold dark matter candidate. Typical mass for it to be the energy density of the universe is 10 to the minus 5 eV, but this mass is very poorly known for various reasons. The axions are the coldest of the cold because their velocity dispersion has nothing to do with the temperature, but has to do with the QCD horizon. If you translate this into velocity dispersion today in intergalactic space or in a homogeneous universe, this is a speed of 10 to the minus 17 times the speed of light. It is 1 centimeter per year. It is 100,000 times less than the velocity dispersion under the same conditions of WIMPs, which is about 10 to the minus 12 or a kilometer per year. Now, I shouldn't talk about temperature, but perhaps I can talk about effective temperature. Because to talk about temperature, you must have thermal equilibrium, and these things are decoupled in first approximation. But you can talk about the typical energy of one particle in an intergalactic space or in the local rest frame of the fluid. And this is extremely cold, it's 10 to the minus 34 degree Kelvin. So to introduce my next topic, I was just going to come back to my pool table. Let's suppose that you had imagined this pool table as a solution to why the pool table is flat, even though the room is cube. And you had tried to do various experiments to excite the oscillations of the pool table, but was never able to produce such oscillations. And you had imagined that the lever arm is perhaps extremely long so that it is very difficult to excite pool table oscillations. You may then have a new brainstorm and say, oh, but if the lever arm is very long, then there are relic oscillations because the age of the universe is finite. And I'm going to look for them by putting an oscillator on the pool table and trying to see whether I can excite this oscillator. Unfortunately, you don't know the oscillation frequency, and so you're going to have to tune it. It's going to be taking a lot of your time. Okay, so this introduces my next topic, which is various techniques to look for axions. How am I doing with respect to time?
20 minutes.
20 minutes left. Okay. So the most mature is the cavity experiment. But there's also almost equally mature, the Axion helioscope. This cavity experiment is called the haloscope because you could, if you had a signal, you could study the halo in great detail. This is the experiment that looks for solar axions. If you had a signal, you could look at the sun in great detail. So it's called a helioscope. Then there are so-called shining light through walls experiments. There are NMR methods. There are axion-mediated long-range forces, LC circuit detector, atomic transitions. And actually, I haven't given you a complete list. I'll even add some more to this to just give you an idea of the number of different approaches that have been proposed. And maybe you can come up with something better yet.
Yeah?
Yes, please.
But maybe before you start with it, I have one theoretical question.
Yes.
You said it's a global U1. So my question is, what is the charge, that is the conserved charge associated with that? And what happens if such a charge falls into a black hole?
So there's a U1 symmetry, that's right. There's a charge associated with it, which is the PQ number. But you realize that this charge is, the symmetry is spontaneously broken. And so it's not analogous really to the electric charge, but analogous rather to the weak charges in the standard model. And actually what that really means, if you have, I have to think about this. So if the symmetry is spontaneously broken, then the charge kind of disappears in and out of the vacuum. Like, like also like the pions, like chiral symmetry in the standard models, because you can produce pions, and they are the Namu-Gilson bosons of chiral symmetry breaking. So only at scales above the Pechi-Quinn symmetry is the charge really conserved in the sense that we think, similar to QCD. So I'm not quite sure this answers your question.
According to the no-hair theorem, in principle, theorists have strong prejudice against global continuous symmetries.
Right. So there has been a number of papers pointing out that if you take the Pechi-Quinn field and you allow some breaking of Pechi-Quinn symmetry due to gravitational interactions associated perhaps with black holes, because Pechi-Quinn charge can fall into a black hole. And you assume that these interactions are power law, then you often find that unless the power law is very large, it will mess up the Pechi-Quinn symmetry. But I'm not too impressed, actually, with these arguments for two reasons. One is that I don't think it's reasonable to, or at least I don't know, I mean reasonable just for my own taste. Here, Spetche-Quinn symmetry is proposed to solve a standard model problem. And here you say, oh, because of quantum gravity and so forth, this cannot exist. I don't know how to weigh these two things, okay, because I don't know quantum gravity. But I do know a Spetche-Quinn solution to the standard model. So I don't know what to make of that. The other thing is that Renata Kalosh, André Linde, Suskind, and someone else at Stanford, whose name I now forget, wrote a paper actually calculating these effects in string theory, which is supposed to be the theory of quantum gravity, and found that it is not power law suppressed, but exponentially suppressed. And in that case, assuming something about the coupling that appears in string theory, these effects are extremely small. And so they said that is well, their answer is that it's not a power law suppression of gravity, the gravitational breaking of Spetche-Quinn symmetry, but an exponentially suppressed interaction. But, you know, it's a matter of how you feel about stuff that we know very little about, I think is fair to say.
In principle, it would probably be enough to say at some very small level this U1 Spetche-Quinn is actually explicitly broken.
I think that's fair to say, yes.
Probably enough to...
Right, I think that's fair to say, because you can have some of the charge fall into a black hole and it just has disappeared. And then you could have the black hole evaporate, and now apparently you have nothing left except that the Spetche-Quinn charge has disappeared. And so it's a breaking of Spetche-Quinn symmetry. But so Kalosh et al., they said, well, this is exponentially suppressed process. I don't know.
So would
Yes,
it be
please.
more natural to look at the coupling of the axions with the quarks?
Yes.
That
Shall I go back to this coupling? Yes, it couples to quarks.
No, I mean more natural because it's coming from the Spetche-Quinn.
Yes.
Charge for quarks. And
Right.
for the gamma, you should, I mean, you have to assume something else, right?
Right. You are talking about the naturalness of this coupling here. Right. Actually, so you're right. The axion naturally couples to the quarks because it is involved in QCD. But actually, it also naturally couples to gamma. And actually, most of the coupling of the axion, the physical axion, is not the bare axion of which I talked originally, because the physical axion is actually a mixture of this bare axion and the neutral pion. So the coupling actually of the axions to nucleons can also be, involves both bare couplings and couplings that are the results of the coupling of the pion to the nucleons. And the same is true with this coupling. So roughly speaking, the coupling of axions to 2 gamma is as little model dependent as the axion of the coupling to the nucleons because of the mixture between the axions and the pi zero. Now, what is true is that this could be accidentally zero because you could have an accidental cancellation between the coupling of the pi naught and the bare coupling. It turns out that in Grant unified theories, you can calculate this, and this is 0.36. In any axion model, it would be kind of artificial to set it equals to 0. But, okay, some number of order 1. Does this answer the question? So. Why not? Why not? Why is not perfect answer? Huh?
No, you answered the question, but I mean, for me, it's more natural to think about the coupling of the axion with the quarks than with gammas. It's right that you can mix it, but as you say, it's more multi-dependent, right?
Right. I'm just saying that for this G gamma to be zero would require an accident. A cancellation, if you want to suppress it by a factor of 0.1, it would be an accident at the level of 10%. If you want to, as far as we know, an accident. If you want to suppress it at a level of 0.01, it would be an accident at a level of 1%. But certainly it's conceivable. I also want to say that in Grant unified models, no matter how the Grant unification happens, this is fixed to be 0.36. 0.36, yeah. So, and the other thing is that, of course, the coupling to two photons is very amenable to experiment. So, one way you can look for axions is to consider the conversion of axions to photons in a magnetic field, which results from this coupling. Similar to Primakov conversion. So here we have a magnetic field, and we put a magnetic field in a cavity, and then the conversion can be resonant because the axion fields surrounding us in this can, if there's a magnetic field, can drive a cavity mode on resonance. And you'll then deposit a small amount of power in the cavity, which can be amplified and digitized and looked for. So it turns out that if you have the cavity of order beta cube and a field of order 8 Tesla and other parameters similar to what you are able to achieve in the laboratory, including a Q for the cavity of order 10 to the 5, you get a power of order 10 to the minus 22 watt, which would seem extremely difficult to achieve, but actually is doable. It turns out people do detect 10 to the minus 22 watt in microwave photons. If the temperature is of order 3 degree Kelvin of the receiver and also the temperature of the thermal noise, then you would be able to search for this signal at a rate of 1 gigahertz per year. So all these are nominal numbers, of course, calculated by a theorist. What the experimentalists do is usually more difficult than a mere calculation. So when the axion converts to photons, because the magnetic field is constant in time, the energy is conserved. So the axion energy is exactly the photon energy, and the photon energy you can calculate, you can measure very precisely. So h nu equals the energy of the axion, which is its rest mass energy, since the axions disappear in the process, plus its kinetic energy. The kinetic energy is of order 10 to the minus 6 times the rest mass energy, because the typical velocity of dark matter axions in the galactic halo is 10 to the minus 3. So the width of this resonance, if you were to see it in an experiment, is of order 10 to the minus 6, the frequency you're looking at. So if you're looking at a gigahertz, the width is a kilohertz, and typically the bandwidth of the cavity is 10 kilohertz. So you're looking for a peak in the noise. And the difficulty is that you don't know where to look. So you have to tune the experiment and try to find a signal. Oops. Oh, I'm sorry, it disappears twice. Okay, there's an experiment called ADMX that has a pretty long history now looking for this signal. And here is an early version of the experiment, early schematic drawing. It was a cavity with tuning rods, and then there's a magnetic field, and the whole thing is cooled, and there is amplifier. This gives you some size of, gives you an idea of the size of the experiment. This is a picture of a cavity. Now the cavity has to be tuned, and so we place rods in the cavity and move the rods. And this is the insert that we have inside the magnet. So this is a picture made by my experimentalist friends, and this is actually not too bad, but often, because we are particle physicists, we think of this like a particle physics experiment, but it's really more accurate to think of it as a radio wave experiment. So in particular, you have to realize that the Axion field, since its velocity is 10 to the minus 3, its Compton wavelength is 1,000 times bigger than the size of the cavity. So it's really a wave. And it's not like the Axion gets caught into the cavity like a WIMP gets caught in a WIMP detector. But still, the Axion fields dry the cavity, some power gets deposited, and then you can spectrum analyze the output from the cavity. And one nice feature about this is that you can spectrum analyze very well. Actually, we can look at the resolution. Sorry, we can look at this. We can look at this peak here, supposedly due to axions, if due to axions, with a resolution of basically 10 to the minus 5. So that if we were to have a signal, we would be able to immediately obtain the energy spectrum of axions, dark matter axions, with a resolution of 1 part in 100,000. And for reasons that I'll explain, we believe that there are going to be narrow lines in the spectrum. And we look for these narrow lines. This is just an exercise where we inject some power and see how well we can detect it. Here is an example also of a narrow line that's injected. And in the high frequency channel, it really shows as a narrow line, like a clock line. The low frequency spectrum is just 1 bit that goes high. So ADMX is in its second generation, was supported by the DOE as one of the second generation dark matter searches, and has become more sophisticated. Here's a picture of some of the people involved. So the second generation compared to the first generation had 2 steps. One was to replace the existing amplifiers by squid amplifiers. Squids are very sensitive devices based upon the fact that if you have a superconducting loop with Josephson junctions in it, if you bias this loop with a current, the voltage that you measure across depends upon the flux that goes through the loop in this way, in this oscillating way. And this is a very noise-free transducer, if you like, of magnetic flux to voltage. So if you bias it somewhere along this curve, you will be able, and you have a microwave photon whose magnetic field flux through the loop is oscillating, it will produce an oscillating voltage. Now John Clark at Berkeley, who is Mr. Squid himself, said he would be able to build these squids that had much better noise temperatures, and in fact he achieved that. The noise temperatures we had with the high electron mobility transistors was like afforded 3K or 2K, but the squid detectors have noise temperatures of order 50 milli-K, which is 40 times better. In fact, they are so good that they are quantum limited. Quantum limited means essentially that you can detect every single microwave photon. So we have installed this now on the detector, but to take advantage of this very low electronic noise temperatures, we also have to cool. And so then we also cool now the detector with a dilution refrigerator. And lo and behold, actually, during the summer, we finally got everything going and we are back into data taking mode. This is what the
size of the cavity from the first generation? Or is it
the cavity has not changed. It's the same cavity as before.
Yes.
Yeah, it's a 60 centimeter size, actually 50 centimeter, 1 meter long roughly.
Okay, and the magnetic field is homogeneous to all the cavity and also the temperature.
It turns out that the homogeneity of the magnetic field is not a big issue. It's relatively homogeneous because the person who built it used to build magnets for nuclear magnetic resonance experiments who liked very high homogeneity, so he naturally builds them. But it's actually not very relevant to the experiment. So we don't worry about that. And it's certainly not perfect. But what matters is actually the integral of the magnetic field overlap with the electric field for the relevant mode. And so this homogeneity is not a big issue. So this is the limits obtained by ADMX in the past. This is what we think we will be able to do. And we are pretty confident, although I think in the first stage we'll only do this. The trouble with this method, which is very mature and we understand it very well now, is that when you go to higher masses, the cavities has to become smaller. And the only way we know how to do this for sure is to have many cavities that are kept in tune and kept in phase. And this is possible in principle, but you can imagine that when you go up in frequencies, this becomes a more and more difficult engineering project. Now also, there is actually an experiment at Yale who right away used the technology of dilution refrigerators and Josephson junction parametric amplifiers, which are similar actually to squids. And they actually obtained the result just last month. Brubaker et al. Steve Lamoureux at Yale is the head of the experiment. And here shows the limit they put. And these are the models, the Axion models, that are, have couplings of order 1 in this G gamma that we were discussing. And they fell a little bit short, but not very much. But also they looked over a very, very small frequency range because the detector is not very big. So this is actually the limit they put is right there. But I hope with the experience now they can propose a bigger detector and start to put limits at higher frequencies.
So, what was the difference that it could go to higher masses? Just the size of the...
Yes, it's a smaller cavity. So it's 4 inches diameter. So that's what made it, and then, it had its tuning mechanism and so forth. Right.
Is there a limitation that made them fall short, or are they just obviously they have to get into the small narrow
Though I think,
range, but can they keep going down? Or what's
no, they could also do equally wide than the others, but they wanted to be sensitive in this stage. They wanted to go down to almost reach the models.
I'm asking, are they limited? Can they keep going down despite?
Yeah, they could go down. If they were patient, they could roll the way down. But the thing is, as you know, you pay a big price in time, right? Because it goes like square root of t. And so after a while, you just run out of patience, right? You're better off rethinking the experiment. So it's very difficult to go down in coupling because, well, the coupling squared is proportional to the signal, and then the limit you put on that only goes like the square root of time. So it's a factor of 4, of a power of 4, more difficult to go down than to go wide. Yeah. 5 minutes, okay. So I want to talk about other experiments and to orient you, because everyone makes a plot that makes their own experiment look good. I want to put everyone on the same plot. My graphics are not very fancy, okay. I'm going to compare some very wide mass range here. The expected mass is 10 to the minus 5 eV. Actually, where we really would like to look is rather on the high range of the cavity experiments. Actually, more or less where the Yale experiment is looking is maybe the sweet spot in my book. But I think it is true that with sufficient resources, this technology being very well understood, it will be able to rule out or see axion, dark matter axions over some range of order, I think about 2 orders of magnitude in mass. And then either the cavity is going to become too big, or you're going to have too many small cavities and you're going to run out. Now, so I want to discuss this bigger plot, because then I can put everyone's experiment on there. So actually, it's maybe a good time to stop. Okay, so we should just do cavities today, and then tomorrow we do other stuff. So thank you for...
Okay, are there any questions? Yeah, over there.
What is the range of the action interaction with this mass scale? What is the range?
What is the plausible range? Okay, so actually, okay, perhaps it's good I go all the way back to my little theory slide, which was very brief. So this is basically my theory slide, okay? It gives the axion mass in terms of the decay constant, and this formula is no doubt about it. This is well established. There's no model dependence here, but there's model dependence in the couplings. So you see, for given mass, you know the coupling, except that there's a factor here, G gamma, which is model dependent and of order 1. It involves a bare coupling of the axions to 2 photons, and also a coupling because the axion mixes with the pion. And so it has a contribution of 2 different origins. And this is what I was arguing earlier. It's an accident that these 2 contributions would be 0. So here are 2 models. One model is called KSVZ. It's 1, and in the other it is 0.36. But you could make other models where the value is different. But I think it is artificial to either make it much bigger or make it much smaller. You have to make the model kind of special. But it has been done. You know, theorists can do lots of stuff if you just challenge them. Yeah, does this answer your question?
Well, yeah, but I think I was referring more to the scale, to the length of the interaction that axions can mediate, or that...
Oh, you mean you're talking about the axial mediation forces?
Exactly.
Oh, I'll talk about that tomorrow.
Oh.
Can you wait that long?
Oh, sure.
So, but you want to know right away, of course, you don't want to wait. If the mass is 10 to the minus 5 eV, the scale is a centimeter. It's a centimeter, right? H bar C is converts 10 to the minus 5 eV to 2 centimeters, actually. So that would be very good. The trouble is if the mass is that large, then the coupling is very weak, because now this FA is 10 to the 12 GeV extremely weakly coupled, and they have not been able to reach such weak couplings. But people, as I'll discuss, they do look for long-range forces mediated by axions. But usually the trouble is that either you have a long range because the mass is small and the coupling is extremely weak, or the coupling is stronger, but then the range is very short, and then you can only do the experiment on a very small scale, and that's also difficult. But people have done such experiments, right? And I'll discuss briefly tomorrow, okay?
Are there any other questions?
My dumbness, but are these experiments that you described background limited in any sense?
Are they what?
Background limited? Is there a background that limits them?
Yes, well, the backgrounds are thermal noise in the cavity and electronic noise. There's no background from cosmic rays, for example.
No, not that type. But the reason I asked this is because when she asked you whether these guys can go down, you said you go down a square root T.
Right.
Whereas you're looking for a signal in a very specific, very peaked signal, right?
Yes.
And this thermal noise is not.
Yes.
So why is it square root T rather than T?
Oh, so okay, so you have a background, and as you say, the background is broad.
Yes.
So you can subtract it, but as you know, you can only subtract the background. You cannot subtract the fluctuations in the background. And that's where the square root of T comes from, really. Is where the fluctuations in the background will average to 0, but only after sufficiently long time. So if you do the experiment on some time scale, there will be some finite fluctuation in the background, and that's the background. But no?
Isn't there like a sideband measurement? Because the signal is in one spot. I agree you don't know where the spot is.
So
or am I misunderstanding?
we can go back to this here. Okay, this suggests a signal. I didn't make the background very big, but usually the background is just as big. See, there is also background, this much background, but that doesn't matter. That you can subtract. But you cannot subtract these fluctuations. Yeah.
And the wiggles you say are as big.
Sorry?
The wiggles are comparable with the signal? Or?
Well, that's for sensitivity, right? That shows how we can see anything that is much bigger than the wiggles in the background.
Okay.
That is actually what sets
Okay.
our sensitivity, yes.
There is one more question over there.
Thank you. Well, recently I've seen a revival on the topic of fuzzy dark matter with axions with a mass of the order of 10 to the minus 22 electron volts or something like that. Can you say something about that?
I was also going to talk about that in the future.
Okay.
But I'm happy to talk about it now. So this is so-called ultra-light axion-like particle. So the axion has a mass of order 10 to the minus 5 eV, but people have invented axion-like particles with mass of order 10 to the minus 22 eV. And as I'll explain probably 2 days from now, this produces wave dark matter. Axions also wave dark matter, but the Broglie wavelength is of order 10 meter in a galactic halo. The cavity is of order 10 centimeter. The Broglie wavelength is of order 10 meters. If you make the axion mass 10 to the minus 22 eV, then the Broglie wavelength becomes of order, I don't know exactly the number, but 100 parsecs. And now the smooth some of the singularities, cuspiness of galactic halos, and helps with the excess of power in the cold dark matter scenario at very small scales. That's the motivation of it, yes. And there's many papers have been written on this, yes, and continue to be written. Even written one by Witten. Did you notice?
That's
yeah,
wicked.
there was a paper by Witten, Oostenrijk, Lam Hui, and Scott Tremaine, actually, 2 weeks ago. And we're writing a paper also about it. But okay.
Thank you. Okay, more questions? So I have the last one then. So the mass of the axion with the with FA, so they basically relate to the ones of the pion, right? So that gives you a band for the,
Yes,
so
yes.
that's for the QCD axion.
Yes, that's a QCD axion.
So that hasn't been ruled out, right? Or has it? Because
It has not
have
been ruled out, no. It's not been ruled out.
I have seen in a couple of talks that people claiming that basically the Axion QCD had been ruled out and it's only the ALP. But because of the
No.
combination, that's not the case, right?
No, it's not been ruled out. I mean, actually, the only thing that has been ruled out is KSVZ coupling over this factor of 2 range by the old ADMX experiment. And then this doesn't actually quite reach the QCD axion. That's the only thing that has been ruled out by the cavity experiment, and cavity experiment is the only one ruling out anything so far. I'll make a list of all the limits. So I'm very grateful to the people who look for WIMS and have made such very good limits on WIMS that now people begin to pay some attention to Axion. So thank you.
So you led me into a question I wasn't going to ask, but now I will.
Okay.
You started out the whole talk saying that axions are cold dark matter.
I'll argue that in the future, yes, soon.
Okay. But related to that,
Actually, I should say more precisely, they are a fraction of the dark matter. I don't think anyone could prove that they found 100% of it, right?
But I mean, the reason you say that is because of the strong theoretical requirement of having such an axion for Peche-Quinn. That is the reason why you think they must be there somewhere.
No,
No. Could you please explain them?
it's because of Bose-Einstein condensation.
Oh, okay. We'll wait.
So, right, I claim that axions actually behave differently. I'll try to make very carefully the distinction, and that the observations support that at least some of the dark matter is axions. Not that people believe me, but I claim I believe it myself, and I'm happy to argue about it.
Okay, this microphone is dead now. Let's give 15 minutes for the coffee break and then we'll come back for the last talk.
Okay.
Right?
Oops.
How Pierre is writing this action.
Yes.